Hi, I'm Zor. Welcome to Unizor Education. Well, this lecture is called Functional and Variation. Well, this lecture is part of the course called Physics Plus for All, which is presented on website unizor.com. Website is totally free. There are many other courses. Math Plus for All. Prerequisite to that is Math for Teens. Prerequisite to Physics Plus is Physics for Teens, and there are other courses as well. I suggest you to use the website if you watch it, if you found it somewhere like YouTube or whatever, because the website contains extremely important part, which video by itself does not. The website presents video and the textual part, which is exactly, well, the same material, just presented as a textbook, basically. Really detailed textbook in some cases. Plus, website has a lot of problems to solve. Exams, by the way, you can control yourself. The site is totally free. There are no ads. You don't have to sign in unless you are trying to study under somebody's supervision, in which case I do need just, some kind of identification to connect your supervisor or parent with you. I do suggest that you use the website, and you will go to this particular lecture, for example, by choosing the course Physics Plus for All. And in this course, the part is called Lagrangian, and this is the lecture in this particular part, the first lecture actually in this part. Okay, now what I'm about to start in this particular part called Lagrangian in this first lecture is to introduce two new concepts. These are two new concepts, functional and variation. These are kind of different than whatever you learned before in physics. Before, you were talking about primarily about the second law of Newton applied to different situations. So if you have something like second law of Newton, which is now A is acceleration, which is the second derivative of the position, right? Well, these are vectors, obviously. Now, if force is constant, then you have a regular polynomial of the second degree, which is a solution to this differential equation, right? If this is a constant, this is the second derivative. So you have twice integrated, you will get polynomial of the second degree. If, for example, function f, force F is proportional to some kind of a distance, like in a spring, for example, the Hooke's law, then it will be some oscillation. It's another differential equation, but still can be solved. It's something like this. Some kind of a coefficient, well, m, whatever, and second derivative of time. Obviously, it's all functions of time. And the solution to this is sine or cosine with whatever the coefficients. Well, what else? Gravitation force. Gravitation force is inversely proportional to second degree of the distance. And again, it will be another differential equation which we were solving in different ways when we're talking about the Kepler system. That's the previous part of this particular course called Physics Plus. The previous part was about laws of Newton, primarily about gravitation. So these are all old methodology which works fine, no problem, but in some cases, for some problems, it does not work. Okay, so let me just remind you one particular problem which we have solved before. Well, if you have a border between two different media, let's say this is a glass, okay, air and glass, and you have a ray of light. Well, there is a refraction. Now, so you have this point and this point. Why light goes this way and not this way or not this way? If you remember, when we were, well, if you don't remember, I'm just telling you that when we were discussing this particular problem, we were talking about Fermat's principle. Fermat was a mathematician, French. And his principle was the speed of light is different in air and in glass. So if you know the speeds of light, you can always find the point that two different segments will produce smallest amount of time, and that would be a trajectory. That's his principle, and the experiment actually showed that this is exactly correct, in which case sines between this and this angle are proportional to ratio of speeds of light in this and this particular medium. Okay, so it's a completely different kind of approach. We are not solving any differential equation right now. We are telling that depending on the trajectory, we will have certain numerical function of this trajectory, time in this particular case. Different trajectories give different time. So whenever we need to find a trajectory which really happens, which light really traverses, we have to use this principle of minimization of time. And if you will, let's say, start from the some kind of a parameter which parameterizes this point, let's say this distance. If you have this distance, you have this distance, you have all distances from both sides, whatever. So you can always parameterize any trajectory, any combination of two straight segments with one parameter, call it h or whatever. And based on this parameter, you can find the lengths of this, divide by corresponding speeds, add together, and minimize as a function of this one parameter. So you're not really considering all the different trajectories. You don't consider this trajectory, for example. You consider only trajectories which have two straight lines. And in this particular case, you can minimize it using the old differential equation approach. But if you will consider something like this as well, then there is no way you can use the some familiar differential equation to describe the time which took the light to go through this particular trajectory from point to point. We need different kind of approach. So we are dealing with time in a more complicated case, when it's not two straight lines. If we consider all the different trajectories which light can take. In this particular case, time is not a function of one particular parameter which you can differentiate by. Time is a function of trajectory. How do you differentiate by trajectory? Well, you have to increment the trajectory somehow and see how time is incremented, right? And then divide increment of time divided by increment of trajectory. Well, that's not easy kind of a thing, because you don't know what increment of trajectory actually is. But anyway, these two things are basically encapsulated in these two words. Increment of trajectory, we will call it variation, and the whole thing, like differential, is the increment of numerical argument, right? dx. Then the variation is increment of trajectory of some other function. Trajectory is a function, right? So basically, variation is an increment of the function, which depends on God knows what kind of parameters. And functional is a function of this function. So the time, if you consider all different trajectories, the time is not just a real number. It's a real number, it's a function which depends on the trajectory, and trajectory is a function itself, let's say of time or something. So you can say that function of function, and that's what's called functional. Now this is a noun. It's not adjective, like functional description of some apparatus, whatever. It's not that. It's functional is a noun. It's like function, but it's a function of not just an argument or a group of argument, like function of three arguments. No, it's a function of a function. A function basically is infinite number of parameters. Okay, now remember this. So in a simple case, we were able to simplify it, right? Okay, so remember this, and I will tell you example of another problem, and how in a simplified version of this problem we can still solve it using the old methodology. So the problem is really simple. You have a river which you have to cross from A to B. River has a current. You have a boat which can go with a speed v relative to water. That's the speed of the boat relative to the water. And then water actually, with a current, moves it somewhere else. But the v itself is the speed of the water, of the boat. Lowercase v would be my speed of the current. Okay, now my purpose is to get from A to B and choose a trajectory which gives me the lowest time. So I can go whatever way. There are many different trajectories. I mean, obviously this doesn't look like an optimal time, but in any case my purpose is to find it. So the time in this case as a function of all possible trajectories is a function null. Okay, and using traditional methodology of differential calculus, I will not be able to do it. So we will delay it until later time, this general problem. With variation I will explain basically how it is. But today I would like to just exemplify how we can simplify the problem, to reduce basically the problem. Instead of all the different scenarios of navigation, I will choose only specific class of scenarios where I am moving the boat along always a straight line with a certain straight direction. And direction would be angle phi. So while I am moving always in this direction, my current will move me to the right. Now, if my direction is correct, in some way correct, my current will move me by the time I will reach the end of this, by the time I will reach the other bank of the river, my current will carry me exactly to the point B. Because if I will aim this way, my current will go to the right and my end point will be here, and then I will have to return back. If I will use a large angle phi, I will go this way and the current will go this way and I will end this way, and I will have to again go and reach my point B. So intuitively it seems that we have to find such an angle, let's call it phi 0, which will bring me to the point B exactly, and maybe it will be actually the optimal point. At least that seems to be, because my my trajectory would be in this case really a straight line from A to B. So let's calculate this angle phi right now. So that would be kind of easy. My vector v, my speed, will have perpendicular to the current and parallel to the current components, right? So if this is my vector v, this would be my v perpendicular, and this would be my v parallel, right? So v parallel goes against the current, and v perpendicular will go across the river. So I will, if the river has width, let's say d, then I know how much time I have to spend to reach my other bank, because I will go perpendicularly to the river with the speed, this one, which is actually v times cosine phi 0, right? If this is phi 0, then this is v times cosine phi 0. d is speed relative to the water, obviously. Now, my parallels to the current speed would be, well, its magnitude would be v times sine phi 0. So what happens? First of all, I have to spend certain time to cross the river to get to some point, right? And the time would be, time perpendicular would be d divided by this speed. Now, during this time, my horizontal speed would be v in this particular direction, but my current will move with the lowercase v. So my actual speed would be v sine v times sine phi 0 minus, that would be my real horizontal speed, right? Now, my real horizontal speed should actually be 0, so I will stay always on this line, right? So this should be equal to 0, and that's the condition when for every movement to the left, current will go to the right, and I will be still on this line, and I will cross it directly to the B. So basically sine phi 0 is equal to v divided by capital V would be my optimal angle. Well, phi 0 is basically arc sine of v over v. In which case time to cross the river would be actually the time to reach point B, because I will reach exactly to the point B. My end point will be B in this case, so it's d divided by v times cosine, which is 1 minus v squared divided by v squared, or d divided by square root of capital V minus lowercase v. So that's my time. And intuitively, it seems to be like the right thing to do. But we have to really think about this. And okay, so what happens? First of all, if we will consider this direction of the angle phi as positive and this direction negative, to go negative really doesn't make any sense at all. Because the more negative you go, your speed across the river would be less and less and less. Because with angle equal to 0, this cosine would be 1. If angle is negative, the cosine of negative is still positive, but less than 1. So the time will be greater. So the more you shift your aim to the right from this direction, so the more negative it is, the more time you spend to cross the river, and then on the top of this you have to return back to the B. So it definitely would be worse and worse and worse. So we should not really consider phi should be definitely greater than 0. Now, let's consider if you have this angle phi 0, which is defined by this, if you will go even to the left from the phi 0, greater, what happens? Well, again, your speed across the river would be lower and lower because you will increase this angle, and you will find yourself further and farther from the B. So first of all, you spend more time crossing the river, and then you have to again catch up basically and go parallel to the bank to the B. Again, worse. So basically only these angles should be considered as candidates. Maybe they are better than phi 0. Maybe. Okay, so we definitely don't want to go this way, so I assume that we go with some angle phi, between 0 and phi 0. Now, what happens in this case? Well, you will reach the opposite part faster. Where? Well, if you aim to this point and current will move you here, if you move to this point, current will move you here. So you will have to return back to the point B. So you will reach the opposite side faster at this particular point. So this is better, right? But then you have to return to the B, and that might be worse. So you have to really find analytically what's really better. So let's try to find analytically, and let's basically find the time to cross the river for any angle phi in this particular range, and what's this distance h which you have to cover, because the current will move you to the right from the B. You have to return against the current, right? So what happens? All right, again. So for any angle phi in this particular range, you have time divided by, depending on angle phi, what it will be, would be d divided by v times cosine phi. Okay, if this is your vector of speed, always constant, then your component which goes across the river would be this. So this is your timing. Okay. Now, while you are traveling, during this time, what happens with your horizontal movement? You move to the left with the speed v times sine phi, but the current moves you to the right, so you have to subtract this. So we really have to assume that since phi is in this particular range, then sine phi is less than sine phi 0, which is v over v. So if this is this particular case, then is it greater or less than 0? That should be, hold on a second, then v sine phi should be less than v, right? If I will multiply this by v, so this should be negative. So to the right, well, we have decided that to the left we have this positive phi and positive h. Now this is negative h. So this is basically the negative. This is negative distance by which we will move to the right. Okay. Now, when now what's the now we have this h, which is distance. I have the speed. So if I will multiply time to cross the river, time the speed by which we are moving to the right all the time, I will have h is equal to t of phi times v sine phi minus v. Well, because it's negative, let's just do with a positive thing. This would be easier. So it's y minus v times sinus phi. Now it's a positive thing, and h now is my, well, consider its absolute value. Okay, so this is the distance. So if I have phi 0, it will be here. If I will have less than phi, it will be to the right. So basically that would be my distance by which I will move to the right of the point B. Again, if my speed, horizontal speed, is this one, well, this is negative, yes, so we change the sign. I multiply by time I have to spend to cross the river. My current will basically move myself to the right by this distance h. Now, what should I do next with this? Well, I have to add the time to return back to B. So I have to, so if this is my time to cross the river, then I have to add time, let's call it time h, which is equal to h divided by the speed when I will move against the current. So what is the speed? Well, it's my full speed. I'm moving right now to the left, minus speed of the current. So altogether, so now everything is positive, right? So we don't have to worry about minus, plus. So altogether, my total time, which depends on angle phi, obviously, is equal to this time, which is d divided by cosine of phi, v, plus this time, which is this, d divided by cosine phi times v minus v sine phi, d divided by cosine is this one times this one divided by v and divided by y minus v. So this is this, and this is this. So it's h, which is this, this is h, divided by y minus v minus c. Okay, so this is my total time. And let's see if there is any angle phi which produce better result than I already have. Now the result which I already have was d divided by v times cosine phi 0, which was d divided by square root of v square minus v square. Okay, but this is one parameter function of phi. So let's just think about what can we do about this function. We can analyze it using the regular differential calculus. So t of phi is equal to, well, common denominator I will multiply it by v minus v. So it will be d v capital minus v small plus d small minus v sine divided by v cosine phi and v minus small v. Well, now obviously this is dv, and minus dv would be only dv capital V minus d, so it would be dv1 minus sine phi divided by v cosine phi v capital minus lower. This v goes down, so we have d divided by capital minus lower 1 minus sine phi divided by cosine phi. Very simple function. So how can we find out what actually, how this function behaves? What is the minimum of this function? Well, very simply, let's just take the derivative of this, and I will tell you the derivative of this t derivative is equal to, well, this is a multiplier, obviously doesn't change anything, and derivative of this is sine phi minus 1 divided by cosine square phi, which is always negative. You see, sine is always less than 1 in this particular case. So it's always negative. What does it mean? If it's negative, it means the function is always diminishing. And the less angle I will make, the greater the function will be. So the function is diminishing, the less argument, the greater function, right? So if I will reduce from phi 0 down to 0, my function will always be increasing. So its minimum value would be wherever I started with phi 0. So that's the solution, and intuitive solution. So whenever you're moving this way and the current brings you exactly to point of destination, that is the best solution. And again, we have solved it without really considering all the possible trajectories. We are only considering the trajectory which maintain constant angle with the straight line AB, and then whenever we reach the other side of the river, we move back to the point B wherever we need. So it's only this type of trajectories which we considered. And the result is that our optimal is such and such. Now, why did I put it this way? Because in some cases, even the sophisticated problems can be reduced to whatever the old differential equation actually is. But not if I would consider any possible trajectory. It's only the trajectories which are related to maintaining constant angle phi with AB, and then returning to B whenever it's necessary. Okay, so I would suggest you to read the text for this particular lecture. It contains basically exactly the same thing, maybe in more details. What else is important? Well, it's always important to solve problems, and I do have some problems in the previous course, the physics for teens, and in the beginning of this particular course, Physics Plus for All. There are many problems. I do suggest you to read and solve all of them. Try to solve it yourself. Okay, that's it for today. Thank you very much, and good luck.